Hello, this is Jack Jackson. We're going to be looking at solving linear equations in one variable today. So we're going to start talking about basic concepts. We'll identify three types of equations: identities, contradictions, and conditional equations. We're going to use algebra tiles to get at some basic ideas of solving equations, and we'll be using the idea of flow charting and applying inverse operations to give us an idea of what order we should be applying steps to solving equations. And we'll do some examples of that, of solving equations by hand. Then we'll use some technology methods, and we'll introduce an intersection of graph method and a calculating zeros method. And we'll do this actually on a TI-84, a TI-nspire, and also in Matica. So we'll use those three particular technologies as examples. And in this video, we're not only concerned with being sure that we have a solid understanding of the skills needed to solve linear equations, but we're also interested in establishing the framework and technique used to find exact and approximate solutions to basically all kinds of equations. So in a way, some of what you're going to see here may be overkill in a bit, that we're going to really go into some more detail than is actually needed for solving linear equations. But if we understand all the techniques and the foundations of the concepts that are going along here, as well as the both algebraic techniques and technology techniques, then we'll be able to illustrate these with this relatively simple class of equations called linear equations, and then we'll be able to use these same techniques and build on them when we get to more difficult types of equations. And in the case of the technology methods, you will see that they will work even when there's not an algebraic method available, at least as far as giving approximate solutions. So an equation is a statement that two expressions are the same. So the equal sign is really the verb is equal to. So when you have that equal to in an equation, it's a mathematical sentence. So you're making a statement. And when equations involve variables, they are statements that are either true or false statements, but they depend on the value of the variable. For example, let's consider a basic equation like 3x plus 2 equals 14. So we can plug in different values of x, and it will either make this statement true or make this statement false. If x equals 2, this implies that 3 times 2 plus 2 is supposed to be 14, or 6 plus 2. Or in other words, the left side reduces to 8 and the right side is 14, but that says 8 equals 14. Well, that's clearly a false statement. So this equation is false when x is 2, so x equals 2 is not a solution to this equation. It makes that statement false. So if x equals 4, for example, we plug that in and try it out. 3 times 4 plus 2, order of operations says multiply first, then add. And so 3 times 4 is 12, plus 2 is 14. 14 equals 14. That's clearly a true statement. So the equation is true when x equals 4, that should say. So x equals 4 is a solution to the equation. I'll fix this to be 4 on the handout. Our goal in solving equations is to find the set of all solutions to the equation. So in this example, it turns out there's only one solution. So when you say 3x plus 2 equals 14, that's true if and only if x equals 4. Now there are three kinds of equations that we might run across. The example we just saw was an example of a conditional equation. It was only true under the condition that x equals 4. So conditional equations, they are equations that are sometimes true and sometimes false depending on the specific values chosen for the variables. Our typical goal in working with conditional equations is to solve the equation. That is, to find out which values of the variables make the equation true. And then we'll list that set of answers. If it's just one number, we'll just say, like in this case, x plus 3 equals 7. It's a conditional equation that's true only under one condition, that x equals 4. So we'll state the solution just that way, x equals 4. If the answer to a different one might be x equals 3 or x equals 5, you could list it that way, x equals 3 or x equals 5. Or you could list it as this way, x is an element of the set containing 3 and 5. And so we can list it in set notation or just as a statement. But the point here is conditional equations, we don't know what x is going out, but we can find out, and that's our goal. X is only one answer, or perhaps a small set of answers, and we want to find out what those answers are. Identities, on the other hand, are equations that are true for all possible values of the variables. When working with identities, the goal is not to solve for the variable, but rather to use the identity to manipulate the form. For example, 2 times parentheses x plus 3 close parentheses equals 2x plus 6. That's an identity. It's an illustration of the distributive property in action. If we think about that as what x's make this true, the answer is all real numbers, or if we want to go further, all complex numbers. And so we see that everything works for this. So this is an identity. It's always true no matter what x is. So whereas a conditional equation is sort of like a mystery, find out who did it, which x's work, which x's are the mystery x's that make this thing work. In identity, that's not the point at all, because all x's work here. We neither know nor care what x is. The point is, every time you take 2 times x plus 3, you get 2x plus 6. So we might write it. We might start with the left side and get the right side, or we might start with the right side and get the left side. Sometimes we'd rather have it factored, like on the left. Sometimes we'd rather have it expanded, like on the right. Contradictions occur when an equation has no possible solution, and the solution set is then the empty set. For example, if we say x plus 1 equals x minus 1, that's a contradiction because it has no solution. No matter what you put in for x, this is always false. We can think of an equation as a balance, with the equals being the fulcrum or balance point. So when we say x plus 3 equals 6, it says that both sides of this equation represent the same amount, 6. It's just written 2 different ways. And so we can think of it as being balanced on the equals. And we can use some physical manipulatives such as algebra tiles and a simulated balance to illustrate some of these basic concepts. And we're going to use that here for a second to help us develop a sense of what's going on as we solve these equations. And I have some virtual algebra tiles I built in Geometry Sketchpad. Okay, so let's take a look at this. So here we have a balance, and this represents x plus 3 equals 6. So the little squares, the purple squares, represent 1, and the light purple bar represents x. It's 1 tall and x wide. Now, this is we don't really know how long it is. Right at the moment, it looks like it's maybe around 4 long, but that's not necessarily what the answer is. We don't know how long to make this bar. So this bar is actually variable in the software. So what we want to do is this is balanced. Both sides have, well, basically 6 items on there, although we have this unknown x representing a certain number of items on the left. What can we do to this balance? Well, one thing we can do is we can add or subtract things from both sides. I think you can probably see exactly what to do here. We want to subtract 3 items from both sides. So, of course, subtracting is adding the opposite, so we can add a -3 to both sides. And the little red squares represent -1. So we can add -3 to both sides, and then the pairs of -1s and +1s that are together on the same side annihilate each other. They're gone. So we can think of adding these -1s and then annihilating them, or we could just think of as a takeaway. Take away 3 of the same thing from both sides. And now we see we have a balance. On the left is x. On the right we have 3 units, so that's 3. And so we see x has to be equal to 3. Okay, so what we've seen is we can add the same constant to both sides of an equation, and after simplifying we have another equivalent equation with the same solution set. So it's quite easy to solve equations of the form x equals some constant equals another constant, x plus a equals b. We can solve that for x pretty easily. So see that the a is attached to the x by addition. How do we undo that? Well, we need to do the opposite, which is subtract a. Okay? And of course, if we subtract it from the left side, we have to subtract it from the right side to keep that equation balanced. Okay? Think of x as like being this little antisocial guy. He wants to be by himself. And he's got this a just hanging on. It's hanging on by addition. We want to get rid of it, we have to do the opposite. We have to subtract it or add the opposite. So, for example, if we have x plus 7 equals 15, just add a negative 7 to both sides, or subtract 7 from both sides. And the 7's cancel on the left, leaving an x by itself. And on the other side, we have 8. And that is our goal, is to get x by itself on one side, to isolate x. So we get x equals, and then the other side is just numbers without x's. Okay, or at least no x's over there. So you can check this by plugging it in. 8 plus 7 is 15. 15 equals 15. That checks. And so we can check our equations that way. The next one, we have x minus 6 equals 21. If we add 6 to both sides, we get x equals 27. And in general, if we have x plus a equals b, add a negative a to both sides, and we get x equals b minus a. Alright, here's another example, very similar example. We have x minus 4 equals 5. So we have an x and 4 negative 1 tiles on the left, and we have 5 positive 1 tiles on the right. We want to get rid of those 4 negative 1 tiles over there with the x. We do that by adding 4 positive 1 tiles there, which means we're going to add 4 positive tiles to the other side. The pairs annihilate each other on the left, and we get x equals 9. Now let's solve a different kind. 3x equals 12. Okay? So we have 3 x's on the left, and we have 12 units on the right. Notice that we can group the 3 x's, say we have 3 groups with x in each group. On the right side, we can organize it so that we have 3 groups also, and I've kind of done that already, so that I have 3 rows with 4 each. So now, if we just pull these in groups of 3 groups, we see that we can divide by 3, which means it leaves us with only one of the groups. So one of the groups on the left is just x, and one of the groups on the right is 4. I got my 3's and 4's backwards here in the write up. The picture's right. I think 3x equals 12. Yeah, the picture's right. So we have 3x divided by 3 is x, and 12 divided by 3 is 4. So this should be x equals 4. Okay, I'll fix that before it's printed out for you. Okay, so we have seen that we can just multiply or divide both sides of the equation by the same non-zero constant, and that allows us to solve equations of the form of a times x equals b for the x. We can think of a being attached to the x by multiplication. How do we undo this? We must apply the inverse operation of division by a, or equivalently multiplying by the reciprocal of a. Again, we must do the same thing to both sides to keep the equation balanced. So if we have 2x equals 16, multiply both sides by 1/2, or divide by 2, and we get x on the left, and that gives us 8 on the right. X divided by 5 equals 35. Multiply both sides by 5 to get x by itself on the left. 5 times 35 is 175. That's a typo. 175. Negative 2x equals 5. Multiply it by the reciprocal, which is negative 1/2, excuse me. And we get, that gives us positive 1x, or just x on the left. And on the right, we get negative 5/2. Or in general, if we have a times x equals b, multiply both sides by 1 over a, and we get x equals b over a. Now this one kind of combines the last two things. We have a 3 attached to the x by multiplication and a 2 attached by addition. So we have 3 x's and 2 units on the left, and it equals negative 4, so we have 4 negative 1 tiles on the right. Now how do we go about doing this? Well, actually you have a couple of choices. You can actually divide first and then add or subtract, but it's much easier if we undo the addition first. And we'll talk some more about this in a little bit. why it makes more sense to do it in that order. So what we're going to do here first is get rid of the 2 first by adding 2 negative units to both sides, and then they annihilate on the left, leaving us 3 x's on the left and 6 negative 1 units on the right, so negative 6. Now I rearranged my negative 1 units in the second picture there into 3 groups of 2 because I have 3 groups on the left. Now I divide by 3 leaves us only one of those groups, and so that gives us x there on the left, and on the right we get 2 units. And by the way, notice I changed the length of the bar of x to be the correct length. It's the same length as 2 units, but it should be negative because it's a negative 2. So we have the golden rule of equations and inequalities. You must do the same thing to one side of the equation as you do to the other side of the equation in order to keep it balanced. Or if we use some good old King James English, thou must do unto one side what thou dost to the other side. So examine what we mean by do the same thing to both sides. Are we allowed to do anything to both sides? What kind of things are allowed? Are there things that we should be careful about? So let's think about that. So recall that a function sends equal inputs, regardless of what they look like, to equal outputs. So if f is a function, we see that if we start with an equation that says a equals b and apply this function to both sides, we're going to get f of a equals f of b. So if we apply any function to both sides of an equation, then we get a new equation. So this says that the solution set of the new equation is a subset of the solution. No, wrong. The solution set of the original equation is a subset of the solution set of the new equation. That's what it should say. That's phrased backwards there. The solutions that you get must contain the solutions to the original. However, we have to be careful to only apply functions to both sides of the equation. But we also need to be careful if f is not a one-to-one function. Remember, if it's not a one-to-one function, we can't reverse this. So f of a equals f of b does not mean that a equals b all the time. Okay, if it's not one-to-one. So it's possible when we apply a one-to-one function that there could be solutions to the new equation that are not solutions to the original equation. These are called extraneous solutions. So it's always a good idea to check your solutions in the original equation. But if you've applied a function that's not one-to-one to both sides of the equation when you're trying to solve it, then you have to check your answers in the original equation, because some of the answers to the new equation may work fine in the new equation, but they may not be solutions to the original. Now luckily this doesn't happen for linear equations, but it can happen for some. And let me show you a couple of examples. So for an extreme example of where we run into problems by applying a function that's not one-to-one to both sides, consider the function f of x equals 0. When we apply it to both sides become 0. Or in other words, another way to do this is say we multiply both sides of the equation by 0. We get 0 equals 0, which is certainly true. The solution set to 0 equals 0 is all real numbers. It doesn't matter what x is, 0 still equals 0. But this is totally useless in solving equations. Certainly our solution set is a subset of the solution set on the right, which is the set of all real numbers. But we've actually lost all of our information. So you want to be careful and do not multiply both sides of an equation by 0, because that loses the information in your equation. Another example of applying to functions not one-to-one both sides, let's consider the function g of x equals x squared. So we start with something that we know the solution of, x equals 5. I mean, it's already solved. But if we apply g of x to both sides, we have g of x equals g of 5, so x squared equals 5 squared, which says x squared equals 25. Now this equation, x squared equals 25, has two solutions, x equals 5 or x equals negative 5. And so just because negative 5 is a solution to x squared equals 25, it doesn't mean it's a solution to the equation x equals 5. So it's an extraneous solution. When you check it, negative 5 equals 5 is false. So you'd have to discard that solution. But x equals 5 is true. So you can apply functions that are not one-to-one, but then you have to check your answers. But we prefer to apply one-to-one functions if at all possible. So a one-to-one function, remember, sends equal inputs to equal outputs, but also these outputs can only come from equal inputs. So if f is a one-to-one function, we see a equals b if and only if f of a equals f of b. So if we apply any one-to-one function to both sides of an equation, then we get a new equation, so that the solution set of the new equation is exactly the same as the solution set of the original equation. So if we can apply one-to-one functions, that's the best. If we have to, we can resort to applying non-one-to-one functions, but then we got to be sure and check our answers. So we only apply non-one-to-one functions when it's absolutely nothing else will work. So luckily there are lots of good one-to-one functions that are useful in solving equations. Adding a non-zero constant, f of x equals x plus c. In other words, adding the same number, constant number, to both sides of an equation. That's a one-to-one function. That's going to be just fine because when our new equation is going to have the same solution set as the original. Now remember that subtracting is adding the additive inverse, so this really includes subtracting as well. Just add a negative if you need to. Multiplying by a non-zero constant a, f of x equals a times x, that's also a one-to-one function. And so dividing is just multiplying by the multiplicative inverse, the reciprocal. So really, whether you call it multiplying or dividing, you can still write it as multiplication. So this tells us that if we multiply both sides of an equation by the same number, as long as that number is not 0, then we get an answer, a new equation whose solutions are exactly the same as the original solutions. We can raise a base to an odd integer power, f of x equals x to the n power, where n is an odd integer, the third power, the fifth power, the seventh power, the negative 1 power. Those are one-to-one functions. And so you can raise both sides of an equation to an odd number power, and you will get a new equation that has the same solution set as the original. However, raising to an even power is not one-to-one, as we saw with the y equals x squared. So if you're going to do something like raising to an even power, like squaring both sides of an equation, you have to be sure that you check your answer. The good news is for linear equations, all we really need is a combination of these first two steps, either adding the same thing to both sides or multiplying the same thing on both sides. So what order do we need to do when we apply these steps when we solve equations? Well, it's going to depend on the structure of the expressions in the equation. So if you can get it into a form of an equation, f of x equals some constant. In other words, all the x's are on one side and no x's on the other side. Then all we have to do to solve it is apply the inverse function for the left side. So the inverse function is one that has the opposite steps in the opposite order. And we're going to talk a lot more detail about inverse functions in Unit 3. But for now, just remember this. You think of the order of operations used in evaluating expressions on the side of the equation with the x's. What order are those steps done? Use the opposite steps in the opposite order, and that will undo them, and we'll solve our equation. Let's illustrate this in an example. It'll make more sense, I think. So if we have the equation 3x plus 2 equals 11, think of just the left side. If you were to plug in an x and evaluate, what are you doing? You're going to multiply by 3 and then add 2. 2 steps. Well, the inverse is to do it backwards. We undo the addition by subtracting 2, then we undo the multiplication by dividing by 3. Notice it's the opposite steps in the opposite order. That tells us exactly what to do to solve the equation. So we have 3x plus 2 equals 11. First we subtract 2 from both sides of the equation to eliminate the 2. So we get 3x equals 9. Then we divide by 3, divide both sides of the equation by 3 to get x by itself on the left, and 9 divided by 3 is 3, so the answer is 3. Of course, you could check it. 3 times 3 is 9 plus 2 is 11, so it does check. So notice that it's the opposite steps in the opposite order tells you how to undo stuff. So you undo stuff in the opposite steps in the opposite order. And so that kind of explains why it's natural to get rid of the 2 first and then the 3. It's just backwards from the order of operations that you would use if you were evaluating this for a particular value of x. In other words, when we check it, we're going to multiply then add. We solve it the other way around. So the steps to solving linear equations, we can just boil it down to some basic steps here. We can simplify each side separately. Okay, that's the first thing we want to do. And get each side as simple as we can get it. Now, here's an optional step that sometimes you can use. Next, if the equation has coefficients that are decimals or fractions, it's often useful to multiply both sides of the equation by a common denominator. That would be a power of 10 in this decimal case, to clear out decimals and fractions. So you could get rid of your decimals and fractions if you multiply both sides by the correct number. And that's sometimes useful, particularly if you're solving these equations by hand. You might want to do it. Maybe even more so useful for fraction equations than it is for ones that have decimals. Okay? But if you're having to do the arithmetic by hand without a calculator, it's oftentimes useful to get rid of those fractions and decimals first. So we can eliminate the variable terms from one side of the equation by adding its opposite to both sides of the equation. And then we can eliminate the constant term from the other side, the side with the variables, by adding its opposite to both sides of the equation. Eliminate the coefficient of the variable term by multiplying both sides of the equation by its reciprocal, and then you're done. And actually, if it's a linear equation, if you don't make any mistakes, it will check. You will not introduce any extraneous solutions because we've only used one-to-one functions in our steps. But it's highly recommended that you check your solutions by plugging them back into the original equation. So let's do a few examples here. 3x plus 2 equals 5x minus 7. Notice I can do basically these two steps at once. I want to get rid of the variable on the right. I want to get rid of the constant on the left. So I'm going to add negative 5x to both sides and add negative 2 to both sides. So negative 5x's and 5x cancels on the right. The negative 2 and the 2 cancel on the left. On the left, we are left with 3x minus 5x, which is negative 2x. And on the right, we have negative 7 minus 2 is negative 9. Divide both sides by negative 2, and we get x by itself is 9 halves, or 4.5. On the second example, we're going to simplify. On the left, we have 3 times parentheses x plus 5, which is 3x plus 15. On the right, we start with the innermost parentheses first and simplify it first. Use the distributive property. Copy down everything that doesn't change, the 5, the bracket, the 4x, the bracket, and the plus 2. And then the part that does change, we write it next. Negative 7 times x minus 3 is negative 7x plus 21. Combine like terms within the bracket to be negative 3x. The rest of it stayed the same. Now distribute the 5. 5 times negative 3x plus 21 is negative 15x plus 105. Before I wrote that down, I would just written everything else down that didn't change. Write everything down again, except this time the 105 plus 2 is 107. Now we've simplified it as far as we can on each side. Get rid of, now it's just like the equation number 1. We want to get rid of the x's on the right and the constants on the left, so we add negative 15, positive 15x to both sides and negative 15 to both sides to eliminate the 15 on the left and the negative 15x on the right. And so that leaves us with 18x on the left and 92 on the right. Divide both sides by 18. That fraction reduces by dividing top and bottom by 2 to 41 over 9, or in decimal form that's 4.5 with the 5 repeating. In the example number 3, notice the one with the most decimal places is 0.25, 2 decimal places. So if I multiply by 10 to the second power, or 1 with 2 zeros, that is 100. On both sides, this will clear out our decimals, and we won't have to worry about the decimals here. Again, this is optional. It's not too hard to do the arithmetic, the same steps that we use for number 1. with the decimals in there, but you know, it might be useful to get rid of them. I'm going to just show you can do that. So we multiply by 100 and distribute. We get 320x plus 70 equals 150x plus or minus 25. So all the decimal places move 2 places to the right when we multiply by 100. Now, no decimals to mess with. We want to subtract 70 from both sides and 150x from both sides. That gives us 170x equals negative 95. Divide both sides by 170. We get x equals negative 95 over 170. That reduces to negative 19 over 34. And that's a repeating decimal that's got a lot of decimal places in it. So I didn't figure that out, but I did write down all the digits my calculator had. So it's approximately negative 0.5588235294112. That answer is less exact than negative 19 over 34. Negative 19 over 34 is an exact answer. The decimal version is approximation. In a similar manner, we can take the two sides of equation number 4 and factor the denominators down into prime numbers. 4 is 2 squared, 9 is 3 squared, and we see that a common denominator for all that, or at least common multiple of all the denominators, would be 2 squared times 3 squared, and so we multiply both sides by that. When we distribute, the first time 1 3 cancels, and we've got 2 squared times 3 times 2 is 24x, and then we multiply it by the next one. The 2 squared cancels. We got 3 squared times negative 1 is negative 9. On the right side, when we distribute, the 3 squares cancel first, and we got 2 squared times 5 times x is 20x. And then we distribute on the last one, the 2 cancels, and we get 2 times 3 squared times negative 1 is negative 18. And so now we have an equation with no fractions in it. Kind of nice. Okay. Again, you could work this by doing the arithmetic just like we did for question number 1, but along the steps you would have to be doing things like adding and subtracting fractions. Not that hard to do, but easier to do this way, I think. So we can add 9 to both sides and negative 20x to both sides, and eliminate the variable term on the right and the constant term on the left, and we get 4x on the left equals negative 9 on the right. Divide both sides by 4, and we get x equals negative 9/4. And we would probably leave it in fraction form since it started in fraction form, but of course that's also negative 2.25 if you wanted it in decimal form. 2 more examples. This one on the left, whenever we simplify all this down, I'll let you look at the steps, we eventually get down to a statement 35 equals 18, which we know is false. If you're working an equation like this and you ever get down to a situation where you get a statement you know is always false, that means you're dealing with a contradiction, and that one has no solution. So the solution set is the empty set. On the right, we have one that eventually we work down to something that's obviously always true. Negative 6x plus 15 equals negative 6x plus 15. Or if you kept going, you might get 0 equals 0 or something like that. Which is always true. Then we have an identity, and so the solution set is a set of all real numbers. X can be any real number, assuming we're limiting ourselves to real numbers. If we're working in the complex number system, the solution would be all complex numbers. Alright, so we should be able to do some of these, solve these equations by hand, but now let's introduce some technology techniques for using things like graphing calculators and maybe some computer programs. There are 2 basic techniques that we're going to go over, an intersection of graphs method and a x-intercept method. So in the intersection of graphs method, these are, by the way, these are both graphical kind of methods, so it will be something we do with a graph. We could do these sort of things by hand with a graph, but the main way I'm talking about here is with technology. So it'll be some sort of technology that gives you graphs and then allows you to do some calculations based on those graphs, like the TI-84, for example. So if you've got an equation, let f of x be the left side of the graph and graph that. And let g of x be the right side of the graph, of the equation, graph that. We have 2 graphs, and we want to know where they cross each other. So make sure your window shows any intersection points that they have, and use your calculator software techniques to calculate the intersection points, and oftentimes these are approximations. And the x-coordinate of the intersection point is what we're looking for. That's the equation to the solution. Now, if they don't cross at all, then you've got a contradiction. If they cross more than once, then there are more than one solution. We have a solution set of multiple points. If they only cross once, then we get a unique solution. When we're looking at linear equations, we're going to get unique solutions, just one. So on the TI-84, here's what you want to do. Let y1 be the left side of the equation. Of course, you've got to use x for the variable if it's some other letter. Let y2 be the right side of the equation. Choose a window that shows the intersection of the graphs and graph them. So you'll graph those. You may need to manipulate the graph a little bit to find where they cross. Once you've got a place where they cross on screen, then press Calculate, which is second trace. Choose number 5, which is Intersect. It's going to ask you for your first curve. Use up or down arrows if necessary to get the cursor on one of the correct graphs that you want and press Enter. When it asks for second curves, use your up or down arrows to choose the second curve and enter. Now, remember, you have to do this because you could graph up to 10 different graphs at the same time on a TI-84. Okay? So, we have to tell it which two we want. It's the intersection of two graphs. Now, if you only have two graphs graphed, it's really easy. Just hit Enter twice. You don't even have to think about it. Then it's going to ask you for the guess. Then use your left or right arrow to move the cursor close to the intersection point and hit Enter. So basically, remember, up and down arrows change curves. Left or right changes the value within the curve. And so then the x-coordinate of the intersection point that it's going to produce is going to produce an x and y point. The x point is the solution to the equation. Now, by the way, the y-coordinate is what you're going to get if you put that x back into the equation. It's going to work down. Each side will work out to be that same y value. So, for example, if the intersection point was the point 2, 3, you plug in the 2 to check, you're going to get 3 equals 3, and it's going to check. But the answer we're looking for is the x solution. So, if you press Quit, which is second mode, and then Math 1 and Enter, you'll get x changed to a fraction, and it will be the same x that we just saw in our calculation. And it will put it in fraction form if it has a nice fraction answer, and so you might be able to get an exact answer in fraction form. So let's look at an example. Here's one worked out. I'm going to actually get out of this right now and show you this actually in action. So I guess we can do the same one. Okay. So if we do the same one, we have 3x plus 4, and then 5x minus 7. I'm going to start with just a zoom 6, a zoom standard. Okay, not a good window. You can see that they're kind of coming towards each other as we go to the right and up, but maybe we need to go, maybe not too much further right, but definitely some further up. So let me go to the right and up a little bit. So I'm going to go up to 20 here, and maybe mark that off in ones. It'll be fine. And then I'm going to go up more. Let's go up to 50 and mark that scale off in 5s and graph that and see if we can see the... Oh, okay, now we can see the intersection point, so that's good. So we have to manipulate this a little bit to find the intersection point. Sometimes it's a little bit trial and error. Let me show you one more thing I did not put into the PowerPoint. If you're looking at the table here, let's see. Let's start at 0, go up by 1s automatically. Okay. If you look here, let me show you something about where you can see this in the table. Okay. Now we're assuming, of course, these are continuous graphs. They're all connected. Look what's happening here. When you're at 1, the y1 is bigger than the y2. Same for 2, same for 3, same for 4, same for 5. Not the same for 6. For 6, y2 is bigger than y1. So that tells me that somewhere they cross between 5 and 6. So which one's on the top? See, y1 was on the top when x is 5. y2 is on the top when x is 6. So they crossed over somewhere between 5 and 6. So just looking at the table, you can get an idea that there is a solution between there, assuming these are continuous functions connected up. Okay, so there's something about the table. But let's go back to the graph. You can actually see it there, and sure enough, that's between 5 and 6. Now, what we want to do now is calculate that. So we go second, and then the trace button, which will be calculate. And we want to calculate an intersection, so we can just press number 5. It's going to ask us for our first curve, hit enter. Second curve, hit enter. We go over close to it and hit enter for our guess. And it turns out it's exactly 5.5. If I quit here and type in x, notice it gives me 5.5. I can go math and hit change to a fraction and enter, and it will change that to a fraction form of 11 halves. Okay, how about on a TI-nspire? 3x plus 2 equals negative 5x plus 1. Okay, we have a slide here about it, but let's look at it. Here's an Inspire. Okay, so you'll want to press the home button, and we want to go to a graph. Okay, so you can use your arrow keys here and press this icon right here. This will add a new graphing window. Okay, and we can type in our formulas here. Okay, so let's do, see, where are we? 3x plus 2 is one of them. So, was that 3? And the x is down here, plus 2. And enter, and there will graph that, and it marks it for us, 3x plus 2. And the other one was negative 5x plus 1. And so we say negative 5. Oops, I need to get this back. Now my calculator, when I have the actual calculator, it has a little button down here in the lower left of the screen I can click on to show where to enter the formulas. But if you don't have that, you can go Control G. You need to remember that. Control G will pull up the little entry there. And so we put in our thing, negative 5x, now I've forgotten what it is, negative 5x plus 1. Something didn't happen right. Let's try it again. Negative 5x negative 5x plus 1. Enter. There we go. And we can see where they cross. And of course, I have the color version of the Inspire, and so these graphs come out in color. And so I want to calculate where these cross. So you just hit the menu button, and we're going to get this here. We use our arrow keys to go down to Analyze Graph, and we want to analyze an intersection point. So we hit intersection, and it's going to ask us for a lower bound, so we go to the left side and hit enter, and then the right side of it here and hit enter, and it's going to come up with our point right there, and there you see it. So it's negative 0.125 is the correct answer. That's negative 1/8 in fraction form. Alright, now how about Matica? So here's Matica. Let me turn off my point tables, clear the screen. And in Matica, we can do the same thing. Well, here, I'll do one. It won't have to necessarily be the same one. So let's say we have 2x plus 4, and we let y equal that. So y equals, and then we could do y equals negative 5x plus 7, and we have that there. So we want to see where these two things cross. So we're solving the equation 2 times x plus 4 parentheses equals negative 5x plus 7. To calculate where the intersection point is in Matica, you go to, I believe it's Tools, and find intersection. Hit enter. From your list, you choose the two equations, negative 5x plus 7, 2x plus 4, and then calculate, and it gives me at least an approximation of that intersection point. One thing that's nice about Matica is it will find all of the intersection points at once. So if you're on a TI-84, for example, whenever you have to go through that process of calc, intersect, choose curve 1, curve 2, choose your guess, and it will find one intersection point. Then you do it again and put this guess next to another intersection point, and then it'll find it. And you have to repeat that process each time if the graphs cross multiple times. Okay? In Matica, it will find all the intersection points in one step if they're on the screen. So all the intersection points on the screen will come up at once in Matica. So that's a little bit of an improvement in Matica. The bad news about Matica is it doesn't show quite as many decimal places as your calculator does, and it won't change them to fraction form. So some pluses and minuses there. Of course, if you have linear equations, two straight lines, either they're the same line, in case it's an identity, parallel lines, in which case there's no solution at all, it's a contradiction, or intersecting lines that are distinct, then there's exactly one solution. So in this section on linear equations, there's only going to be exactly one solution if it's a conditional equation. Okay, now let's look at another possibility here. We want to do the x-intercept method, so we can eliminate everything from one side of the equation, okay, and get 0 on one side. So now you have some expression with x on the left equals 0. Let f of x be that thing on the left and graph that. Then we use our calculator software to calculate the x-intercept of the function, and the x-coordinate of the x-intercept, also known as a 0 or a root, is the solution to that equation, and that's what we're looking for, is the x-coordinate of the x-intercept. So here are the steps on a TI-84. Again, eliminate everything from one side of the equation by adding the opposite to both sides and get it in the form f of x equals 0. Let y1 be whatever's on the left side, the non-zero side. Graph it. Choose a window that shows the x-intercepts of the graph. Could be more than one. If it's linear, they'll just be 1. And then press Calc, which is second trace. Choose number 2, which is a 0. It's going to ask you for a left bound, a right bound, and a guess. For the left bound, first of all, use your up or down arrow to make sure you're on the right curve if you have more than one curve graphed. Okay. Again, right or up or down arrows, choose the curve. Left or right, choose the point on the curve. So again, if you've only got one equation graphed, you won't have to worry about the up or down arrows, but use your left or right arrow to go to the left side. Another way to do it is to actually type in a number at that point. For example, if you know -1 is to the left of it, you can just type in -1 rather than trace over there with the arrow key. Similarly, you either type a number in or an enter or right arrow and then enter to get a right bound. So make sure left bound's on the left side of where it crosses the axis, right bound's on the right side where it crosses the axis. Then move. So let's see, where were we choosing? We choose 2, 0, then left bound, right bound, and a guess. And of course you want to make sure that your x-intercept is between that left bound and right bound, and you want to try to get your guess fairly close to where it crosses the axis. It's a lot better if there's only one solution between those left and right bounds. When you're finished, you can press quit, which is second mode, and then when you press X, that gives you your X value again. We looked at this before. Change to a fraction if you want to get a fraction solution. So let's look at this in action for a particular example. I'll do the one that goes along with the video here with the PowerPoint. So here what we want to do is solve for 0 first. So get 0 on the right side by adding -8 to both sides. We can simplify or not. We can say 3x plus 4 minus 8 and leave it like that. Or we can go ahead and do a little bit of work in our head. 4 minus 8 is -4. And so we can write this as 3x subtract 4. And I'm going to clear out this other equation. And I'm just going to graph this one thing. Let me just do a zoom standard here and see. Yeah, that just works out nicely. We can see the x-intercept there. So we're looking for this point right here where it crosses the x-axis. So we do second calc. We want to calculate, that's called a 0. That x-coordinate of the x-intercept is called the root, or a 0. So we're going to click enter. Asks us for our left bound, so we get here kind of close to it, but on the left side, hit enter. Then we go over here, right arrow to the right side. Okay. Or if we know, for example, if we know that, say, 4 is on the right side, we could just hit 4 and enter. So you can do it by entering a number or just an arrow keys. And again, you can enter your guess by entering a number or your arrow keys. But try to get this pretty close to y is 0, close to where it crosses the x-axis. And then hit enter and we'll return that. So it looks like it's 1.3 repeating. Okay, of course y should be 0 or extremely close to 0 when it works this out. Should be exactly 0 really, but on occasion it works out something very, very close to 0. And so we get this. So if we quit and type x, it will give us that 1.3 repeating. If we hit math and then enter, it will change that to a fraction, 4/3. Okay, let's do the same thing on the Inspire. Okay, so let me hit Control G again to see my graphing window, and I can go up here and get rid of some stuff. Let's see here, I think I can get rid of that one. No, it didn't. I can at least turn them off like this. Okay. Let's just replace one of these. So let's see. Well, we'll go ahead and do the same one that's in the PowerPoint. 3 times x plus 2 equals -5x plus 1. Just add a 5x and a -1 to both sides. And we got 3 times x plus 2 plus 5x minus 1. So 3x plus 2, 3 parentheses x plus 2, close parentheses, whoops, we don't need that, there it is. Let's see again, plus 5x and minus 1. Plus 5x is down here, minus 1. Okay, and we want to turn that graph on. Whoops, should have hit enter is what I should have done. Plus 5x minus 1 and enter. Okay, and so it graphs it, and we want to find where it crosses the x-axis right here. So notice it shows us this formula down there with the label. Okay, it's got a point on there right at the moment, but we want to find this place where it crosses the x-axis. And so, come on, there we go. And so we go to our menu and analyze graph, and it's going to be a 0, the first one here. Hit enter. Again, it's going to be left bound, so use your arrow keys. Get to the left side, hit and the right side, and hit enter, and it's going to come up and tell us our point, 0.625. Okay. So that's the Inspire version. How about this version here? Okay. If we want to find, let's just say we've got an equation in here, anything we want. Let's say this one here. And we want to find where that crosses the x-axis. So we're solving 2 times x plus 4 equals 0. What we can do is go to calculus and say find critical points. And hit enter. And notice it says we have a 0 at x equals negative 4. Of course, y being 0. So it's actually x equals negative 4 is the solution there. Nice thing about this one is, on the critical points, it will find, not only will it find the zeros or x-intercepts, it will also find the maxima, local maxima and local minima all at once. All the maxes, all the maxima, all the minima, and all of the x-intercepts that are on the screen, it will find them all at once with that one command. So that's pretty nice. Okay. So here's Matica. Oh, Matica has something else that you can do. Let's say we want to, this is kind of a little different here. Suppose we've got the equation, and our equation looks like 3x plus 7 equals 4x minus 5. And it just looks like that. You can type it in just like it looks. Now that's an equation that only has x in it, so it will actually solve for x and graph that, which is a vertical line. And that vertical line is at the right place. It looks like it's around 12, but we can look at our point tables here and see what the x is over here on the right, and it's exactly 12. So 12 is the correct solution to that equation. So that's a Matica solution, that a different solution is that you don't really have on the other technologies. Finally, one more thing. If you've got the CAS version of the Inspire, you even have one other way you can do this. And this is, you just tell it to solve it. So you go to a calculator screen, and you just go to your menu, and under Algebra, the first thing is Solve, and you just type your equation in. 3x plus 2 equals 5, comma, x. Tell them we want to solve that for x. And hit enter, and it'll solve for x. If you have an equation that has x's and y's, you can solve it for x or y using this same technique. You just the comma x tells it what you're solving for, and it will work this out. I think I've got another example of that here on the. There's an example there. This particular example, I did something a little bit more complicated. Okay, you can see the menu structure there. It's Algebra Solve. Type it in, then comma x, and it gave my answer in fraction form. But if I, instead of hitting enter, if I hit enter, I get the first one. If I hit control and enter, I get approximation, which is down here. This is only on the CAS version of the calculator. Okay, so what kind of goals and objectives we have? Well, after studying this lecture, you should be able to explain the basic goal of solving equations and inequalities, classify an equation in one variable as conditional, identity, or contradiction, know what those things mean. We could talk about how to use algebra tiles to demonstrate the basics of solving equations, and maybe use that to explain to somebody what's going on here. Understand the importance of the order of operations and inverse operations in solving equations, and know what steps we have to do in what order to solve the equation. And of course, solve some equations, solve some linear equations. We'll get to inequalities later in one variable, and state and graph the solution set. And use calculators and computer technology also. Not only can you solve them by hand, but also you can use calculator and computer technology to use the intersection of graphs method and the calculating zeros method.